Hey everybody, we're going to talk about binomial probability distributions. Binomial probability distributions. And there's four criteria in order to have binomial probability distributions. The first is that the procedure has a fixed number of trials. Second, trials must be independent of one another. Third, each trial has two outcomes, and we label them as success or failure. And the fourth one, probability of success is always the constant. It's always the same. It doesn't change between trials. And one thing I want to point out is for whenever the trials must be independent, you can apply the 5% guideline for cumbersome calculations. And that means that if your sample your sample size is no more than 5% of what your population is, because it's such a small number, you can sample without replacing and still treat it as though it's independent. Because remember, whenever I sample without replacement, I now have a dependence. I change my sample space as I go along. But since it is such a small percent of the overall population, you may treat it as independent. Okay, so for this section, you'll need to know the criteria to have binomial probability distributions. And there's four criteria. The next thing that you'll need to know is how to read the binomial probability distribution table. And it is Appendix 1A in your book, so you can find that and use that. I also have the table on my campus. So, simple set of instructions. And you'll see that reading the table is actually very simple also. First, locate n, and n is your fixed number of trials. Next, you'll locate the corresponding x value, and x represents the specific number of successes that you're wanting. And last, you're going to move across to the desired p-value, and that p-value represents the probability of success in one of n trials. And one thing I want to point out to you is that for the table that Triola has in the book, and you need to use that because there's rounding in other tables. So use his, that way you get the correct answer whenever you type it in. Cannot be used for values of n greater than 8 or probabilities not listed, and I'll show you that on the table. So I'm going to pull up the table here. And we have table A1, binomial probabilities, and it goes from, there's our n value, and it goes from 2 to 8. There's our x values. So we have our fixed number of trials, n, and it'll have a corresponding x. X is the specific number of successes that I'm wanting within the fixed number of trials. And then across the top are my probabilities. And you'll see these are common probabilities or just tenths. But 0.01, 0.05, 0.1, 0.9, 0.95, 0.99 are common ones, and you'll start seeing that trend as we work through the remaining chapters. But then they break everything else down by tenths. They could do this for any number, they could have this table, but our table would just be massive. It'd almost be easier just to plug into the probability formula instead of being able to locate each one and track it down. So, if I had, for instance, let's say 4 fixed trials, and I want to know the success of 2, okay, with the probability of 0.5. The first thing I would do is I would find 4 for my n, and then I would go to 2 for my x. And then I go across until I match up with the probability of 0.5. And that is my probability answer right there, 0.375. Now it's easy for me to talk it, so, but it's better for you guys to be able to visualize it, so that's what I'm saying. What we have here, this is one thing I find cool about the statistics problems, is that they're actual especially in Trello, they're actual studies. So with this one, this example, we're going to use table A1, appendix 1 out of your book, and it's the binomial probability distribution table. And here's our problem. It's based on a Harris poll, 60% of adults believe in the existence of the devil, assuming we randomly select 5 adults. So there's 4 questions, A, B, C, and D. The first one says, what is the probability that exactly 1 adult believes in the devil? Well, with these problems, the first thing that I do is I write down everything that I need. And I know I need N, X, and P. Alright, so in my initial problem, I have this. That's going to be my probability. I'm going to convert it from a percent to a decimal, so 0.6. And then it says, assuming we randomly select 5 adults, and that's going to be my N, so the number of trials. And then my particular question that says, what is the probability that exactly win? So that's the only thing that's going to change. X, the value of X in this problem. So now all I'm going to do is use my table. I had N is equal to 5, right? And X is equal to 1. So 5 and 1, and my percent was 0.6. So I go across until I hit 0.6. I'm at 0.077. See, now slide to the left. See, there's my 1. I started off with my fixed number of trials is 5. My specific number of successes for this problem was 1. And my probability is 0.6. Now I'm going to scroll up and show you. And there's my 0.6, or 60% of the adults. And so that is my answer. And it is simple as that. My answer for that was 0.077. So as a percent, that kind of helps me be able to see it. 0.7%. Okay, now the next one is 5 adults. Well, I already know N. I know X because it gives it to me in 3. And my probability is so 5.6. So there's my N value of 5, my X value of 5, and I scroll over to 0.6. And the answer is 0.78. Now, what I'm going to point out, you notice these two are about the same. With distributions, and you probably remember, or distributions would go something like this. And what we're looking at along that, and this is a crude representation. This is just an overview. Sorry, it's even crooked. But, what I'm ranging from is 0 to 5. And what I'm looking at the 1 and the 5, so we're dealing with very small portions. Just scaffolding our learning for what is to come. Okay? The next one, it says at least 3 adults. So with that is N equals 5, X equals 3, and P is 0.6. So the key thing is at least. So visualize that in case you get caught up in it. We know we're ranging from 0 to 5. 3 is somewhere in here. At least 3. I need to make at least $3. At least 3. That means it's a minimum. I need to make at least 3. So what that entails is that at least 3 deals with 3, 4, and 5. 3 is my minimum, and 5 is the maximum in this case. My number of fixed trials. So 3 to 5. So I need to look up all 3 of those. I need to find for x equals 3, x equals 4, and x equals 3. And then I need to sum them together once I find those. So, to the table, 5, then we'll do 3 first, and that is 0.346. And I'll switch back over after we go through all of these. And then 4 is 0.259. And 5 is, and we already found 5, 0.078. And I corrected my error on the up here. I wrote 0.78, so 0.078, sorry. Alright, so here are my 3 values, and all that I do is add them together. Messing up my math. This is my answer for at least 3. And then no more than 3 adults, or no more than 3 adults. We're looking at the opposite of at least 3. Again, ranging from 0 and 5 to 10 to 12, so here's 3. I want no more than 3 people to come over. And no more than 3 people to travel in the car. We need to save in something in which we generally will talk about it. So I'm looking at those 4 values. And for sake of time, I'm going to go ahead and just write the information down. Okay, whoops. Let me slide it up some so you can see it. And there is our answer, 0.663. Okay, guys, that is finding your probability of success for the given number of trials and the specific number of successes for this problem. And it's just using table A1 to be able to do the math. So really all you have to do is be able to find it on the table, and then if you need to, sum up with notes. Remember at least and no more. Also, go back and make sure that you remember the criteria to have binomial probability distributions for criteria. Alright guys, continue to watch Publishers videos, critically think and structure your homework, and good luck on the remaining homework.